Hello friends, good afternoon and welcome to Decide Live Lectures. Dear friends, today in chemistry we will be talking about characteristics of polymers. To discuss this topic we have with us our subject expert Dr. Sushila Singhal. Dr. Singhal is Assistant Professor in Department of Chemistry in Deshbandhu College, University of Delhi. Without further ado, I would like to welcome ma'am to our studios and request her to start the lecture. Welcome ma'am.
Thank you, Amriji. Good day viewers. In the previous lecture, we have discussed about the classification of polymers, its introduction and how these polymers have been classified on the different properties like its structure, its stereochemistry, its molecular forces and many others. And we have discussed also the mechanism of polymerization, the real reactions which is going place in the preparation of the polymers. Today we will divide our lecture into two modules. In the first module, we will first discuss about the characteristics of properties which include the molecular weight determination of polymer and the methods of polymerization which will include the condensation polymerization, and in the addition polymerization the bulk polymerization will be there, suspension polymerization, solution polymerization and emulsion polymerization, that how these polymerization practically will take place. Then we will discuss the glass transition temperature and the melting temperature of a polymer and various factors which will affect the glass transition temperature and the melting temperature of a polymer. In the second module, we will discuss about some addition polymers. One of them will be the polyethylene, its preparation, its properties and the application of polyethylene. Then we will discuss polypropylene, polyisobutene, Teflon, a very important polymer on the basis of its commercial applications, and the polystyrene. Then we will discuss all these addition polymers, their properties and the application part of these polymers. So, starting with the molecular mass or molecular weight of a polymer. Molecular mass of a polymer is quite different from that applied to the small sized compounds, because these polymers are polydiverse, polydisperse and quite heterogeneous in molecular mass. In other words, we can say that polymers are mixture of molecules of different molecular masses, since many monomers are present in a particular polymer. Now, three main types of molecular mass of polymers has been recognized till now. One of them is the number average molecular mass, weight average molecular mass and the viscosity average molecular mass. So, what is this average molecular weight? The average molecular weight for any chemical substance is the total weight of the sample divided by the number of moles present in a particular polymer. You can see in the equation that this is the molecular weight, and we will find out the sample total weight of the polymer, which will be divided by the number of moles of monomers present in that sample. So, polymers are the complex mixture of molecules of different molecular weights. These polymers are heterogeneous in nature, that is, all molecules are not of equal size. One monomer can be of small size and the other monomer can be of bigger size in case of condensation polymers. They vary in size and thus their molecular weights also different. Therefore, an average molecular weight is to be calculated, which includes one of them is the number average molecular weight. In polymer science, the average molecular weight is discussed earlier, and which is called the number average molecular weight and is denoted by the Mn. This Mn is the ratio of total weight and the number of polymers present. To get the formula for Mn, we must realize that molecular weight distribution is not a continuous function of M. The possible values of M are the various multiples of the monomer molecular weight by monomer molecular weight, which mean the weight per monomer that appears in the polymer chain. The possible values of M or the molecular weight made up of a set of number with the discrete value labeled as Mi. Now, let Ni be the number of polymers with the molecular weight Mi. Then the total weight of all the polymer will be represented as summation of the total number of this I is the number of monomers present. So, it will be a summation of total n number of molecules and the molecular weight of the all monomers. So, total number of polymer molecule will be equal to, will be represented like this. So, number average molecular weight will be the ratio of these two properties, where capital N is the total number of moles present in the molecule and the small ni is the number of moles of imers, that is the total number of monomers present. Then comes the weight average molecular weight. Now, consider a polymer property which depends not just on the number of polymer molecules, but on the size or on the weight of each polymer molecule. So, a classic example is the light scattering example, in which we will take the weight average molecular weight. For such a property, we need a weight average molecular weight. Now, total weight of a polymer sample will be can be represented as W, which will be the equal to the summation of the Ni and Mi. Weight fraction of fraction I or fraction 1 will be equal to the N1 M1 divided by the summation of Ni Mi. Now, molecular weight contribution by fraction A will be the ratio of these two properties, and the average of these molecular weight will be equal to the fractions of addition of the fractions of all the properties present together. Now, by noting the Xi I Mi ratio with respect to the Ni Mi is the weight fraction of polymer with molecular weight I. This I is the number of moles of the monomers. Now, it is denoted by the Wi, then the weight average molecular weight in terms of weight fractions will be given by the equation you can see in the slide. This is the equation, final equation. Then comes the next method of molecular weight determination, which is a viscosity average molecular mass. In this viscosity average molecular mass, we will take the viscosity parameter, viscosity measurements of many polymers, and then we will compare the viscosity data of all the polymers which are in the range of that molecular weight, which will be given by the molecular weight of depending upon the viscosity, which is the mv. It will be equivalent to the ratio of these two properties, and here this A is a constant. The viscosity and the weight average molecular masses are equal when this A is a unity, or it is equivalent to 1. Now, to show these three molecular weight determination, we have shown you some examples. If a polymer sample has population of many monomers, like 10 molecules of a particular monomer with the molecular mass 5000, second is a 20 molecules of molecular mass of each 7500, 20 molecules of molecular mass 10,000, 25 molecules of molecular mass 15,000, and like all. Now, you have to calculate its number average and the weight average molecular mass of the polymer. Now, what we have to do for calculating the number average molecular mass of the polymer, we have to add the total number of molecular masses multiplied by their number of molecules present, and we will sum up these all and will be divided by the total number of moles. These are the total number of moles present, then we will get a ratio. Here in this particular case, we will get a ratio of 1.3 into 10 raised to power 6 divided by 100, and we will get the number average molecular weight 13,000 in this case. Then in the second step, we will take the weight average molecular mass of the polymer. In the weight average molecular mass, we will multiply the number of moles with the square value of the molecular mass of a particular monomer present divided by the total molecular weight of that polymer, and we will get the answer 15480. This will be the weight average molecular mass of the polymer. In the second example, we have shown you how you will calculate a number of particular monomer molecules present depending upon its degree of polymerization. So, the example is that 28 grams of ethylene was polymerized, and average degree of polymerization of polyethylene so produced was found to be 500. So, you have to calculate that how many numbers of polymethylene molecules are actually used to get this degree of polymerization equivalent to 500. So, in this case, how you will solve this problem, that degree of polymerization is equivalent to the ratio of number of ethylene molecules and the number of polyethylene molecules formed. So, now you have to calculate this value. So, therefore, the number of polyethylene molecules formed will be equivalent to number of ethylene molecules divided by the degree of polymerization. So, from these equation we will get the number of polyethylene molecule, in this case found to be 1.2046 into 10 raised to power 20 molecules. So, based on these equations you can solve these type of problems. Then comes the method of polymerization, that how a particular monomer combines in which manner to get a particular polymer. The conversion of monomer into a polymer is a exothermic process, and if heat is not dissipated or properly controlled, then explosions may result. The polymerization techniques employed are different for addition and for the condensation polymerization. This is basically due to the difference in the mechanisms in the two type of polymerization which we have discussed in the previous lecture. So, consequently, main polymerization techniques used for these two type of polymerization processes are discussed separately. First, we will discuss the condensation polymerization. It is conducted at high temperature as well as low temperature. So, in case of high temperature method, this method is commonly used industrially because it is the first method to be developed. In this method, monomers in suitable stoichiometric proportions are mixed in an autoclave and heated at a high temperature and pressure. Then a viscosity stabilizer, which is also called as blocking agent, is also usually added to the extent of 1% together with the delustering agent. Here delustering agent used is a titanium dioxide. As the reaction progresses, the viscosity increases and the volatile products, which are normally water, finds difficulty in escaping from the reaction mixture. Now, at this stage pressure is released, followed by the application of vacuum and heat more strongly to complete the reaction. Now, as the polymerization get completed after several hours, the entire mass is pushed out from the autoclave very quickly, quenched in water, cut, washed and dried. In order to achieve a high degree of polymerization, the extent of reaction must be high. This technique required monomers of high purity, at least 95% purity should be there in a monomer. To get the product free from impurities, side reactions and degradations, stoichiometric equivalence must be provided. Now, in order to avoid oxidative degradation, the reaction should be conducted in an inert atmosphere. If oxygen is there, if any other atmosphere is there, then there may be some oxidation or degradation reaction may happen. The second method is a low temperature method. In this method, the monomers are heated separately to a high temperature to provide them the requisite amount of energy for activation. Then they are mixed, then these two monomers are mixed, or maybe 3 or 4, 5, and stirred till the reaction is complete. If the monomer reactivity is high, then the reaction can be conducted even at a lower temperature. For example, to produce nylon 6,6, if instead of adipic acid, its acid chloride is used for reaction, then the polymerization takes place at the ordinary temperature. You can see in the example that for the preparation of nylon 6,6, we have taken hexamethylene diamine, and instead of taking adipic acid, we have taken here its activated stage, which is the adipyl chloride. Now, this activated adipyl chloride, it will react with the hexamethylene diamine and will undergo condensation to give polymer, which is called as the nylon 6,6. Now, after condensation polymerization methods, next is the addition polymerization. The selection of a polymer technique for the production of polymers on an industrial scale is based on several technical and economic factors. Most important addition polymerization techniques are only 4. One is the bulk polymerization, second solution polymerization, the third one is the suspension polymerization, and the last one is the emulsion polymerization. Now, we will discuss all 4 categories in separately. So, first of all we will discuss about the bulk polymerization. In bulk polymerization, the monomer is used in undiluted form. There is either no solvent or very little of it. The polymer being insoluble in the monomer separates out as a solid mass. The polymerization reactions are generally exothermic and large amount of heat of reaction is generated during bulk polymerization, which leads to certain side reactions. In recent years, progress have been made in this direction to control the temperature conditions, and these difficulties had been overcome by special designs of reactors and agitators. So, to control the reactions, we have to design the apparatus or the many other techniques used in the bulk polymerization. This polymerization involves the use of both monomer and the initiator as the main components. The process is generally carried out by a continuous process which involves two stages. First one is the pre-polymerization and the second is the post-polymerization. So, in the first stage, it is carried out in a nitrogen atmosphere in a reaction vessel which is heated by a hot vessel or hot water coils, and the monomer is added continuously with stirring at certain rate into the vessel when the monomer is polymerized to about 30%. In the second stage, the post polymerization, the polymerization mix, which is the highly viscous and clear, is fed into the upper end of the vertical reactor, divided into the zones, each kept at desired temperatures by means of superheated steam, except the lower one, which is electrically heated, to get maximum heat necessary for complete conversion of monomer. The average residence time in the respective zones decides the successfulness of the process because the viscosity increases with the polymerization. The highest possible conversion of the monomer is carried out in the lower zone, and the resulting molten polymer is taken out with the help of an extruder unit conveyed through conveyor belt over an air or water cooling system, followed by chipping and grinding of the solid polymer. Alternatively, the molten polymer is extruded into rods or fabricated into the sheets. By these technique, polystyrene, polyvinyl chloride and PMA are produced. Then comes the second method of polymerization, which is the solution polymerization. In this polymerization, as the name itself explains, solution of monomer is used. The solvent may be an inert one. This method is normally used for moderating the rate of a chemical reaction. If the polymer as well as the monomer is soluble in the solvent, then the solution will be stirable, and if the polymer is insoluble in the solvent, a stirable slurry will be formed. These techniques, it involves in first dissolution in a suitable solvent and then initiator is added to start the polymerization reaction. The heat of polymerization is mostly dissipated by evaporation, followed by condensation and recycling of the solvent, and after the required extent of the polymerization, the polymer produced is precipitated by an suitable non-solvent to the mix. The solid polymer is then filtered off, washed free of any adhering monomer or solvent and dried before use. The polymerization of N-vinyl pyrrolidone, acrylonitrile, acrylic acid, etc. is also carried out by this method, wherein water is used as a cheap solvent for this polymerization. Then the third method of polymerization is the emulsion polymerization. In this method, monomers are dispersed as fine droplets. The size of the droplets is about 10 raised to power minus 5 to 10 raised to power minus 6 millimeter in a large amount of water, and then emulsified or stabilized by the addition of a soap or detergent or any other protective colloids, which can be casein, can be gum, gelatin or dextrin. And after adding this monomer and the emulsifier, then the initiator is added in the third step. Then these the initiators are usually of redox type, which may be either water soluble or monomer soluble. Very often persulfates are used, which give rise to sulfate ion radical. These ion radicals, they interact with the monomers in the emulsion or micelle form, and the polymerization finally occurs. The emulsion is used as such if used as adhesive, surface coating or textile finishing. Alternately, polymer emulsion may be broken by adding an electrolyte, which can, or it may be a solvent, followed by washing, drying, etc. of the coagulated polymer. This emulsion polymerization method is widely used to prepare vinyl polymers, which contains the double bonds, which is an unsaturated polymer like PVC, polyvinyl chloride and polyvinyl acrylonitrile, etc. This method combines the advantages of bulk and the solution techniques, namely rapid production of polymer, ease of temperature control and high average molecular weight. So, this production of polymer, ease of temperature control and this high average molecular weight, these advantages are only in the emulsion polymerization. Then comes a suspension polymerization. This polymerization was developed with a view to improve and simplify the emulsion polymerization method. The monomer is dispersed as relatively large droplets with the particle size of 0.1 to 1 millimeter in water. It is kept in suspension by mechanical agitation, and then the catalyst is added and the initiation takes place. As the polymerization proceeds, as it propagates, the viscosity of the dispersed drops increases and they becomes sticky. Now, at this stage, suspension is stabilized by addition of a small amount of suspension stabilizer, and the suspension stabilizer may be kaolin, it may be magnesium silicate or aluminum hydroxide, etc. Otherwise, the droplets will agglomerate together and drip away, thus breaking the suspension. Now, when the reaction is complete, the reaction product in the form of pearls is washed to remove the stabilizer from the surface of the polymer, then it is dried, and then these polymers are used in case of suspension polymerization. This method is widely used to prepare many industrially important polymers like PVC, PVA and polystyrene. The next important property or characteristic of polymer is the glass transition and melting temperature. Now, what is this glass transition? This glass transition stands for the change in the appearance of the polymer. The glass transition occurs generally in amorphous or glassy polymers when upon cooling from the liquid, crystallization does not take place, that is the polymer chain are unable to rearrange into a three-dimensional long range ordered structure. Now, if crystallization will not take place, then what will happen? Upon cooling, the glass transition corresponds to an increase in viscosity, and because of increase in viscosity, a rubbery or a resinous material will be formed. The gradual transformation from a liquid to a rubbery material and finally to a rigid solid resin-like substance is the glass transition. And the glass transition temperature is the temperature at which the polymer experiences this transition from rubbery to rigid states, and is termed as the glass transition temperature, which is designated as Tg. Now, melting and the glass transition temperatures are important parameters relative to applications of polymers. They define respectively the upper and the lower temperature limits for numerous applications, especially for semi-crystalline polymers. Moreover, they also influence the fabrication and processing procedures for polymers and polymer matrix composites. The temperature at which melting or the glass transition occurs for a polymer are determined from a plot of specific volume, and this specific volume is the reciprocal of the density versus temperature. Now, in the plot you can see that curves A and C are for the amorphous and the crystalline polymers respectively, and for the crystalline material there is a discontinuous change in the specific volume at the melting temperature Tm. You can see the plot, this curve A and curve C. The curve A is for a glass material and curve C is for the crystalline solid, and curve B is a semi-crystalline solid. The curve for the totally amorphous material is continuous, but it experiences a slight decrease in the slope at the Tg. Now, the behavior is intermediate between these extremes for the semi-crystalline polymer, which is the curve B, in that both melting, and this is the melting temperature and this is the glass transition temperature, both melting and this glass transition temperature, these phenomena can be observed in the semi-crystalline solid. This Tm and Tg are the properties of the respective crystalline and the amorphous phases in this semi-crystalline material. Then comes the factor influencing the melting temperature. This melting temperature is the temperature at which the polymer completely melts into a liquid. During melting of a polymer, there occurs a rearrangement of the molecules in the transformation from ordered to disordered molecular states. Molecular chemistry and structure will influence the ability of the polymer chain molecules to make these rearrangements, and therefore will also affect the melting temperature. And what are the factors? One of them is the chain stiffness, which is controlled by the ease of rotation about the chemical bonds along the chain. It has very pronounced effect on the melting temperature. The presence of double chain bonds and aromatic groups, which lowers chain flexibility and thus causes an increase in melting temperature. Furthermore, the size and the type of side groups also, the substituent present also, they also influence the chain rotation, its freedom and its flexibility, which also affects the melting temperature of a particular polymer. The bulky of the large size side groups, substituent present, they tend to restrict the molecular rotation and thus raises the melting temperature. If we take the example of polypropylene, it has a higher melting temperature than polyethylene. Why? It is because in case of polypropylene, we have a methyl group in a side chain. So, methyl side group for polypropylene is larger than the hydrogen atom which is found in the polyethylene. So, it will have a high melting temperature. One of the other factor which also affects the melting temperature is the presence of polar side groups, which can be chloride, hydroxide or cyanides. Even though not excessively large, it leads to significant intermolecular bonding forces and thus relatively increases the melting temperature. And this may be verified by comparing the melting temperature of polypropylene and polyvinyl chloride. In case of polypropylene, there is no polar group present, and in case of polyvinyl chloride, chloride is present as a polar group, which increases its melting temperature. Degree of branching also affects the melting temperature of a polymer. It also increases, it lowers the melting temperature. Then comes the factors influencing the glass transition temperature. Again, the chain flexibility is diminished in case of glass transition, and this Tg is increased by the same factors which affects the melting temperature, that is the presence of bulky side group, the polar side group or group of atoms present, double chain bonds, and increasing the molecular weight also tends to raise the glass transition temperature. Some amorphous polymers which are cross linked, which has been observed to elevate the Tg, they cross links and they also restricts the molecular motion. So, there are many factors which increases the glass transition temperature and the melting temperature of a particular polymer. Thank you. welcome back. After discussing the characteristics of the polymer, now we will discuss some individual polymers starting from the addition polymers. In case of addition polymer, we will discuss about the polyolefins, which will include the polymers belonging to the unsaturated monomers. In case of polyolefin, first of all we will discuss the polyethylene, which is a very common polymer present towards all around. It is also called as polythene. So polyethylene can be polymerized from ethylene monomer and is also known as polythene. Two variety of polyethylene or polythene are prepared commercially. One of them is the low density polyethylene, that is LDPE, and one is the high density polyethylene, that is the HDPE. At present, 65% of the global production of polyethylene is the low density polyethylene, while high density polyethylene is only 35%. Now comes the method of preparation, that how we will prepare the polyethylene from ethylene. Ethylene is a gas which is first liquefied under high pressures, which is up to 1500 atmospheres, and then pumped into a heated pressure vessel, which is maintained at a 150 to 250 degrees centigrade temperature. Then by catalytic effect of traces of oxygen present in the vessel, the ethylene is polymerized into the polyethylene, which is a waxy solid which comes out from the perforation in the bottom of that vessel. This is the equation, that how ethylene polymerizes to make the polyethylene. This is ethylene monomer. It polymerizes via addition polymerization mechanism we have already discussed, and then it converts into a polymer. Now by using free radical initiators, low density polyethylene is obtained, while if we use ionic catalyst, then we will get high density polyethylene. Now first of all we will discuss low density polyethylene polymer preparation. It is prepared by methods which involves the use of high pressures, which is about 150 to 350 megapascal. The polymerization is initiated by the free radicals producing agents such as benzoyl chloride, benzoyl peroxide, azo bis isobutylonitrile, or it may be oxygen. And there are three steps in the mechanism. First is the initiation, then propagation, and the last one is the termination of the reaction. In case of initiation, it may be brought about by either heat, sunlight, or by the sunlight. Initiation gives rise to free radicals. So free radicals in the first step will be generated. This is the benzoyl peroxide. It will decompose on heating or by sunlight, by ultraviolet rays. First it will convert into these free radicals, which after decarboxylation will convert into a further free radical. Now these free radicals, they will combine with the first number of monomer, then they will propagate the chain. One of the other initiator is the azo bis isobutylonitrile, which also decomposes, and nitrogen is released from this initiator, and now this free radical, it will propagate the chain. The second step is the propagation of the reaction, which involves the addition of this R free radical, which is generated from the first step, to the ethylene monomer to give an initiated monomer radical. So in the propagation step, this free radical, it will attack on the 1 mole of ethylene to give the initiated monomer radical. Now it will propagate the chain. The new radical then adds to more number of monomer molecules to form a polymer chain. These are the propagating step. This is the initiated monomer radical. It will attack on the second mole of the ethylene, and then it will grow the chain in a growth initiated monomer radical. Then it will add on to the n numbers of ethylene molecule to give a n number of molecule in a initiated monomer radical chain. And in the last step, these monomer radicals, they will undergo termination to make the final polymer, and this termination can be achieved either by combination of these radicals or by disproportionation method. So, in case of combination, the half of the chain of this radical, it will combine with the other half of the chain of the free radical, and we will get a combination polymer. In case of disproportionation, one of the product formed will be the polyethylene and the other one is the alkane will be formed in this case. Then comes a high density polyethylene. The high density polyethylene is produced by various methods. Polymerization is conducted in the presence of Ziegler-Natta catalyst, usually based on titanium tetrachloride and the aluminum alkyl. For example, diethyl aluminum chloride can be used in the polymerization of HDPE. The reaction is carried out in an inert atmosphere, usually of nitrogen. Here the ethylene, the catalyst and the diluent such as heptane or toluene are continuously fed into the reactor, or all the three molecules will be thrown into the reactor, the temperature being maintained at 50 to 75 degrees centigrade. Then the polymer formed is sparingly soluble. It forms then a slurry which is continuously removed from the vessel. The reaction is stopped by the addition of alcohols such as methanol or ethanol. And finally, the removed slurry or the polymer is centrifuged, it is dried, it is extruded and then granulated. The polymer so obtained has less branching. Then comes the properties of polyethylene polymer. This polyethylene or polyethylene is a rigid, waxy, white and translucent material. It exhibits considerable chemical resistance to strong acids, alkalis and salts at room temperature. However, it is swollen and permeable to most oils and organic solvents, particularly kerosene. It is a good insulator of electricity, and due to its high symmetrical chain structure, polyethylene crystallizes very easily. The degree of crystallinity may vary from 40 to 95% depending upon the degree of branching in the polyethylene chain. Polyethylene produced by high pressure process has a branched structure and therefore is much flexible and tough. On the other hand, low pressure process results in a completely linear polyethylene having higher density and better chemical resistance. Polyethylene is polar and is an inert material. The oxidation of polyethylene sometimes occur in air at elevated temperatures. So, the oxidation, it lowers the molecular weight of the polymer and thus results in deterioration in mechanical properties. Therefore, in the preparation of the polyethylene, antioxidants are generally added to the polymer to avoid the oxidation reactions. Polyethylene may also be cross-linked by exposure to high energy radiations such as X-rays and gamma rays. Then comes the application or uses of polyethylene. Polyethylene is one of the major commercial polymers and is used in such diverse applications as chemical plant, domestic goods, electrical insulation, packaging films and toys, etc. Film application accounts for about 70% of the low density polyethylene production, while injection molding and blow molding take about 75% of the high density polyethylene production. Polyethylene is widely used for the manufacture of articles such as molded containers, lids, jars, bottles, radio and television cabinets, toys and many other household items. Cross-linked polymers find some application as cable insulation, which is subjected to elevated temperatures. Then there is a very important issue regarding the polyethylene, which is the environmental and its health issues. Although ethylene monomer, which is used for the polymerization, it can be produced from the renewable sources, but generally this polyethylene is made from the petroleum or the natural gases. Now, the major problem of polyethylene is that without special treatment, it is not readily biodegradable. and thus it accumulates in air, it accumulates in soil, it accumulates in water, in the whole atmosphere, causing the major cause of pollution. The effect on health includes the direct toxicity, as in case of lead, cadmium and mercury. It is carcinogenic also, as in case of diethyl hexyl phthalate, and it also causes endocrine disruption, which can lead to cancers, which can lead to birth defects, to immune system suppression and the developmental problems in children. Then the second addition polymer is the polypropylene. It is not possible to prepare polypropylene by using the high pressure free radical processes of the type as we have used in case of polyethylene, because the resulting allyl radical it is a resonance stabilized initiator. If you see the equation, which is the initiation step, that when the free radical it will attack on the monomer of the polypropylene, then the initiated monomer radical, this radical is a resonance stabilized of two structures. So, it is very difficult to isolate the one of the structure from these resonance stabilized structures. So, this polypropylene will not undergo polymerization based upon free radical. Polypropylene is prepared commonly by a slurry process as used for the preparation of polyethylene with Ziegler-Natta catalyst. In case of polypropylene, some atactic polymers is also formed beside the requisite required isotactic polymers. So, in case of atactic polymers, there is no specific rearrangement in the polymerization of polypropylene. In liquid phase processes, polymerization is conducted in liquid propylene at 2 megapascal and 55 degree centigrade temperature. Pressure and temperature has been controlled. This is the equation in which this monomer propylene it polymerizes to give us the polypropylene polymer. Then comes the property and application of polypropylene. The physical property of polypropylene resembles those of high density polyethylene, but there are some significant differences. Since the mode of preparation of polypropylene and high density polyethylene are same, so there are some similarity in the physical property. Polypropylene has increased softening point and therefore has higher maximum service temperature. The tensile strength and stiffness is maintained at elevated temperatures. At 140 degrees centigrade, polypropylene is sufficiently stiff, whereas polyethylene is molten at this temperature. So, this is the difference in the stiffness of these two addition polymers. The solubility of polypropylene is similar to that of polyethylene. Thus, polypropylene is insoluble at room temperature, but soluble in hydrocarbons and chlorinated hydrocarbons at temperature higher than 80 degrees centigrade. This polypropylene is more prone to attack by oxidizing agents because the presence of the tertiary hydrogen atom at the alternate carbon atom. Therefore, here also antioxidants are added in the polymerization of the polypropylene to avoid the deterioration, to avoid the decomposition of the polymer formed. Now, when polypropylene is exposed to high energy radiations, cross linking occurs to give a more useful material. After polyethylene, polypropylene is now an important commercial polymer. It is being used mainly in the injection molding of many articles as luggage, steerable hospital equipments, storage battery cases and washing machine agitators. Polypropylene films also finds application in the food wrapping. Polypropylene fibers are also used as a tufting material in the carpets, which can be indoor, which can be used for the outdoor purposes, in the preparation of handbags, blankets and aprons, etc. Polypropylene is also used for making water pipes, etc. Next addition polymer is the polyisobutene. Polymerization of isobutene can be carried out only by cationic polymerization. Aluminium chloride and boron trifluoride are the preferred initiator for the commercial preparation of the polymer. This is the equation in which the monomer isobutylene in the presence of boron trifluoride and water, it will polymerize to give us the polyisobutylene. The solutions of isobutene or isobutylene and boron trifluoride in liquid ethylene are mixed on moving belt so that the polymerization takes place slowly and heat is removed by vaporization of the solvent, since the solvent here is a water. The polymer is then mixed with an alkali or ethanol to deactivate the initiator and treated with steam to remove water soluble materials. Now, at ordinary temperatures, the polymerization is extremely rapid and it leads to the formation of low molecular weight polymers, which are viscous oils or sticky solids. However, the reaction is carried out at low temperature, approximate 80 degrees centigrade, to give the high molecular weight material. Continuous processes are also employed in which only small quantity of the reactants are involved at any moment. Now, we have shown you the mechanism of preparation of polyisobutene. The first step is the chain initiation. In the chain initiation, proton from boron trifluoride and water adds to the carbon-carbon double bond of isobutylene to give a stable tertiary carbonium ion. The tertiary carbonium ion is the most stable carbonium ion among the all three secondary, primary and tertiary carbocations. So, here a stable carbocation is formed in the first step. Now, this tertiary carbonium ion in the second step will add to the another isobutylene molecule monomer to form a new carbonium ion, which can add to the another molecule of isobutylene and then another and then so on, and we will get a long chain of these carbonium ion radical. Now, this will undergo chain termination by the loss of proton. A proton will be lost from the carbonium ion and a butene will be formed in the termination step. The one of the other step may also take place in the termination, that any nucleophile will attack on the carbonium ion and we will get a different product in case of chain termination. Then comes the properties and applications of polyisobutene. Polyisobutene with average molecular weight approximate 1500 is sticky viscous liquid, whereas its high molecular weight polymer, which is approximate 1 lakh to 2 lakh molecular weight, these polymers are rubber like resembling crepe rubber. Polyisobutene is non-crystalline when it is unstretched and is therefore insoluble at room temperature in hydrocarbons. The polymer is resistant to most acids, alkalis and aqueous solutions of salts. It is more resistant to oxidation than polypropylene. However, polyisobutene is susceptible to thermal degradation as the resultant tertiary free radical has greater stability. So, here the chances of oxidation is less and there is a chances of degradation of this polymer by a thermal process. A limitation of this polymer is its tendency to cold flow. As a result, the polymer finds little use in self-supporting form. The main application of polyisobutene are as adhesives, fibers and paper coatings and blends with the other polymers also. It is also used as an insulation material. Next addition polymer is the Teflon, which is also called as polytetrafluoroethylene. Teflon is a trade name. It belongs to a unique class of vinyl addition polymers. Now, what is different in these polymers? It is important among fluoroplastics. Fluorine is present in Teflon, a very highly electronegative atom. These fluoroplastics, they provide chemical inertness over wide temperature range, insolubility in all solvents, high mechanical strength and it's resistant to abrasion. Although fluorine and hydrogen fluoride are highly reactive, fluorine compounds, but fluorinated hydrocarbons are inert chemical compounds. The reason for this is that the carbon fluorine bond is much stronger bond than the carbon hydrogen bond. As a consequence of their physical properties, the fluoroplastics are used where other polymers could not hold up. So, before discussing its polymerization, first we have to synthesize its monomer also, which is the tetrafluoroethylene. So, for the monomer synthesis, tetrafluoroethylene, it starts from chloroform, which involves 3 steps. In the first step, first this chloroform is converted to a mixture of dichlorofluoromethane and chlorodifluoromethane with hydrofluoric acid in the presence of antimony pentachloride. Then this dichlorofluoromethane, it gets converted into the chlorodifluoromethane in the second step. And lastly, the pyrolysis of this chlorodifluoromethane, it comes here at 600 to 800 degrees centigrade with platinum as catalyst, and here in the last step tetrafluoroethylene is formed. So, the monomer synthesis starts from chloroform itself in the presence of hydrofluoric acid, and via a different sequence it finally forms the monomer in the last step. Then this monomer in the second step will undergo polymerization. So, Teflon is obtained by polymerization, polymerizing the tetrafluoroethylene in an aqueous medium, in a where water is a solvent. Since tetrafluoroethylene is a gas at room temperature and the reaction of polymerization is highly exothermic, it is polymerized free radically under pressure. The reaction is catalyzed either by oxygen from air or by the addition of peroxides in water. The water used helps to dissipate the heat which is produced during the polymerization. So, here is the n number of tetrafluoroethylene which will polymerize in the presence of peroxide along with water and will finally convert into a polymer which is called as the polytetrafluoroethylene, also named as Teflon. Then comes the properties of Teflon. Due to the presence of highly electronegative fluorine atoms and the regular configuration of the polytetrafluoroethylene molecules, it results in very strong attractive forces between the different chains. These strong attractive forces, they give the material extreme toughness, high softening point, exceptionally high chemical resistance toward all chemicals except for the hot alkali and the hot fluorine. Towards its high density, its waxy touch and very low coefficient of friction and extremely good electrical and mechanical properties. It can be machined, it can be punched, and these Teflon can also be drilled. The material, however, has a disadvantage that it cannot be dissolved and cannot exist in a true molten state. Around 350 degrees centigrade, which is its softening point, it sinters into a very viscous opaque mass which can be molded into certain forms by applying high pressure. Then comes the application of Teflon polymer. It is used as insulating material for motors, transformers, cables, wires and fittings, etc. It is also used for making gaskets, packings, pumps parts, tank linings, chemical carrying pipes, tubings and many other tanks in equipments. It is also used for coating and impregnating glass fibers, asbestos fibers and clothes, and in the non-lubricating bearings and non-sticky stop cocks which can be used in burette and many glass apparatus also. It is used as a coating of frying pan in the non-stick kitchen utensils. That non-stick coating is of Teflon polymer. In the pipes and the valves that handle the corrosive liquids and which seals to replace the metal and the rubber parts. Then one more addition polymer is the polystyrene. The polymerization of styrene was observed in 1839 when a solid product was obtained on heating the monomer. It was with styrene that H. Staudinger developed the theory of polymerization as the chain reaction. Now first we have to synthesize the styrene molecule itself, which is a monomer synthesis. This styrene is synthesized almost exclusively by the catalytic dehydrogenation of ethyl benzene, which is obtained by a Friedel-Crafts reaction of benzene with ethylene. The dehydrogenation of this ethylene benzene is catalyzed by metal oxides at 600 degrees centigrade. This is the benzene. In the presence of ethylene, it undergoes Friedel-Crafts reaction to first give the ethyl benzene, which then will react with the metal oxide, and a styrene monomer is produced in this reaction. The separation of this styrene from divinyl benzene is very important, otherwise cross-linked polymers will be obtained. So, in order to prevent the premature polymerization of styrene, sulfur and dinitrophenols are added before distillation, and tertiary butyl catechol is added before its storage. Now, for the polymerization of styrene, it can be easily polymerized by free radically. It can be polymerized equally well by cataneically, aninically, or with the complex catalyst also. So, this is the molecule of styrene, which in the presence of benzoyl peroxide will undergo free radical mechanism and will polymerize to give us the polystyrene molecule. Then this polymerization of styrene, it can be carried out either by bulk solution suspension or emulsion polymerization by any method of the addition polymerization. The suspension technique for manufacturing of polystyrene is also widely used. In this, the liquid styrene containing a free radical catalyst is dispersed in water so that the suitably sized droplets are formed. On heating, this styrene polymerizes to beads, which is the polystyrene beads. The polymerization of styrene with aninically and Ziegler-Natta, they produces the isotactic polystyrene. Then comes the properties and application of styrene. It is used mainly for the injection molded articles, for example household containers. It is used for highly oriented monofilaments, for example brush bristles, and highly oriented films for insulation purposes. Co-polymers produced by suspension polymerization, they yield pearls which are used as ion exchange resins after sulfonation. So, there are many applications of polystyrene polymers which can be used. Now comes a few questions based on today's lecture, that how you will determine the molecular weight of a polymer, what is the number average method and the weight average method, explain the various method of polymerization, the glass transition temperature and the factors which will affect the glass transition and the melting temperature of a polymer, and the different type of addition polymers. Thank you.
Dear friends, due to paucity of time, we have to stop our lecture here. On that note, we would like to thank Dr. Singhal for coming to our show and delivering this wonderful lecture. And thank you, dear friends, watching our show. Stay tuned and keep watching. Thank you.